Okay, this is power factor correction. Work with power factor, etc. So, what is power factor? So, briefly, you have an AC circuit, and here's our XY. And I'm going to draw volts in blue. So we have our voltage, and it's some AC voltage like that. And it goes on theoretically indefinitely. So we have our signal like that. It's at some height. Then our power factor, if we have a power factor of 1, then our current is perfectly aligned with our voltage. Because, as you know, though, you should, if you've gotten to this point, you should know that the current through an inductor, and or a capacitor, it has an effect on the phase angle of the voltage and current. So for as an example, this problem, I'll use dark green to show our current. The current is lagging the voltage due to an inductive load. So we have the current lagging at a point at 0.6, which, as we get into this lesson, will mean something more. So, kind of explain what it is. Here's that too. Let's work on the problem now. Okay, so the problem is a load absorbs 500 volt amps of power at a power factor of 0.6 lagging. Now, some people might be listening to this and have never heard of volt amps. A volt amp is similar to wattage, and we'll get into how it's similar. But the volt amps takes into account your imaginary power, and we'll kind of get into that as well. So we have our volt amps, or we have a load absorbs 500 volt amps of power at a power factor of 0.6 lagging from a 240 volt RMS 60 hertz power line. Find the effective RMS current drawn from the source. So to do this is our simple Ohm's law, which is V equals IR. In this case, or our power circle, which is P equals I times R, or sorry, not I times R, sorry. I times V. So we know that 500 is equal to some value I times our VRMS. So 500 divided by 240 equals our I, which in turn yields 2.08 amps. So we've answered part A. There's part A. Let's erase. Clear all my drawings. There we go. That's better. Okay. So now we want to find the ideal capacitor that should be placed across the input of the voltage terminals to correct the power factor to 0.093 lagging. And I think it's important here to note our power triangle. So we have a right triangle here. We have our VA as the hypotenuse, our volt amps, which equals apparent power. I'm going to put app power. And then we have this right here, which is our, on the cosine, well, it's on the x-axis, is our real power. And then this, our y-axis is, I'll draw it right here so you still see the problem, reactive power. And then this right here, theta, is our power factor. Okay, so this is important to remember right here when working with these problems. So now that I've explained that, given our power factor is equal to 0.6, we find our theta, we need to find our theta, and our theta is equal to cosine -1 of 0.06, and which in degrees is equal to 53.13. Now, wiping it assumes 53.13 degrees. So if we go back to our triangle here that I just drew, we have our theta here of 53.13 degrees. We know this is 500. This is 500. So then we just need to find our real. Real is going to be equal to 500 cos 53.13 and reactive is equal to 500 sine 53.13 degrees, which conveniently is equal to 400, and our real power is equal to 300. So our S is equal to 300 plus J 400 VA. So I have to remember that for later. Clear. So that's what we have now. But we want our power factor to be 21 point, or we want our power factor to be 93. So what is 0.93? Well, same cosine -1 of 0.93 yields the angle of 21.57 approximately degrees. So now we have what we need in a triangle. This 300 stays constant. We know that our original value is 400, but what do we need to add to this, or our Q cap, in order for this theta to be 21.57? So to find the Q cap is equal to 300 tangent 21.57 degrees. Minus 400. Which is equal to negative 281.43 bars. So we now will clear this. In my drawing, we need 281.43 bar. So we have this value. So the formula for finding our C, our capacitance, is equal to Q cap. I wish you would recognize. Q cap divided by omega VRMS squared. So we already found 281.43 to be our Q cap. We just know from it's given here, these values, 2 pi times 60 times 240 squared. And when you actually put this into a calculator, punch it out, you end up with 12.96 microfarads. So that is how big of a capacitor you need. That is the answer to part B. So now part C, find the effective current. And this is why you would put in, you want to correct your power factor. So clear my drawing. So now we know 300 divided by 0.93 equals 322.58 volt amps. Let's verify that. So I'm punching it again into my calculator right now. Divided by 0.93. Yep, so we have 300 divided by 0.93 equals this. Then we have 322.58 divided by our 240 VRMS. And we find that a corrected power factor yields us 1.34 amps only. So compared to our original was 2.08 amps, and 2.08 minus 1.34 times 240 means we are using 177.6 less volt amps, which is a significant amount of power saved by just having a correct power factor. And that's it. So we solved a problem and shown the benefit of having a good power factor.